Hello, my name is Kamal, and today I'd like to go over this wonderful book called "Scaling Down to Scale Up: A Guide to Parameter Efficient Fine Tuning." At this point, this paper is more than a year old, but it's highly relevant, and I really like two things about it. It defines a really nice taxonomy of the methods, and it has very succinct explanations of each of those, and it's really easy to follow along. So let's jump right in. Basically, what is parameter efficient fine tuning? So they start by noticing that the model sizes have grown significantly faster than GPU memory has grown. For instance, the original BERT paper said, 12 GB of GPU memory at context length of 512 tokens was not sufficient to fine tune BERT. And of course, it has only gotten worse since then. So the basic idea of parameter efficient fine tuning is that since the amount of memory needed during training is a function of the number of trainable parameters, apart from being a function of the total number of parameters, uh, it varies significantly by the number of trainable parameters because you need to compute and store the gradients, you need to store the first and second moments of the gradients for the optimizer state, and a bunch of other bookkeeping information that are training time overhead. And this can typically be more than 20 times the amount of memory that you need for inference. The basic idea of parameter efficient fine tuning is that rather than fine tuning or rather than optimizing all the parameters of the model, if you only optimize a very small subset, and typically this is much less than 1% of the parameters, then the amount of GPU memory that you need ends up being significantly smaller, thereby making it practical to fine tune much bigger models on lower end GPUs. And of course, if you reduce the amount of memory required, then if you're doing distributed training, now your communication overhead is minimized and so on. Not to mention that you risk overfitting much less than you otherwise would. So that's basically the idea of parameter efficient fine tuning. And what this paper does is to survey several approaches for what they call PEFT, short for parameter efficient fine tuning, and they classify them into five categories. Of course, these are not absolute because their boundaries can get blurry at times. But they classify them and then they select a few from each categories and describe them. So let's do that right now. Let's see, as background, it'd be good to recall what a transformer block is. You may remember that in a transformer block, you have the single biggest thing that made transformers work, the multi-head attention block, which basically has the feed-forward networks that compute Q, K, and V, and this is followed by and of course the attention-based aggregation of the values, which are then fed into something that accumulates the residual piece plus, or sorry, this is the residual that accumulates the original X and applies layer norm on it, and similarly another residual loop, another loop to aggregate X in the residual, followed by feed forward network and layer norm. Right, so this will be really important when you try to understand how adapters work and so on. So, okay, let's jump into the taxonomy part. So here basically they classify these into five types of methods. The most common is additive, So here basically you add a small number of parameters and you tune only those parameters. And the different methods vary in terms of how you add them, where you add them, and how you train them. Of these, there are two significant classes. One of them is called an adapter. These are basically methods where you add small layers at specific parts of the network. And soft prompt is a really nice idea where you take this discrete optimization problem of finding good prompts and you make it continuous by actually learning parts of the prompt rather than specifying it manually. And then you have, and of course there are a set of methods that kind of are additive but are neither um, adapters nor soft prompts. Then there are selective methods which are very intuitive. Basically, you use some criteria to select a subset of parameters that you want to update. And an extreme case of this is something like bitfit, where you only select the biases. Or there are other methods where you can be much more discriminative in the parameters that you select. And then you have reparameterization. These are very popular, especially LoRa and Krana. What you do here is you do update a bigger set of weights, but you do that through a small set of weights. So basically, you make the big set of weights a function of a smaller set of weights, or the updates to the big set of weights a function of a small set of weights. And in both LoRa and Krana, you do this by deriving a low rank approximation for the updates that you want to make, and the two approaches differ in how you do the factorization. And we'll get to that in a minute. And of course, there are a number of approaches that fall on the boundaries. There are hybrid approaches. There's something called S4 here, which uses all the tricks, or it borrows from many of these approaches. And also UniPel borrows from a lot of these approaches. But this framework of thinking of these in terms of additive, selective adapters, soft prompts, and reparameterization is really helpful when you look at a new approach. Now we can jump into each of these here. They basically give you a high-level overview of each of these, but we can jump into the details right away. Let's see. This is the empirical part. We will get to this soon after we look at what the individual methods are. Let's see. So we can start with additive methods. As you saw a minute back, adapters are one kind of additive methods. What happens here is, actually the easiest way to explain this is to look at this pseudocode. Again, if you remember the transform block that we just looked at, most of this should be familiar. Oops. Most of this should be familiar. But then here you see that after the self-attention block, you have a tiny FFN that's been added. And after the second FFN, there's been another one added. And of course, this is followed by layer normalization and the skip connection that you saw. So what's happening here? What's happening here is that all of the parameters of the model have been frozen except for this FFN here and this FFN here. And they show that empirically this works really well. It's kind of surprising. I had initially thought that you would need to initialize these to be somewhat close to identity for them to work, because you don't want to corrupt the representation at a very fundamental level. But it turns out that you do not need to initialize them very carefully. They can be randomly initialized, but since you're freezing the rest of the network, it still works. AtomX is, since you know this, it's relatively straightforward to understand, except So what they do in Atomix is they use the idea of mixture of experts, or if you're familiar with ensembles, that is what this is, but they use it in the context of adapters. So maybe, again, the easiest way to explain this is by looking at the pseudocode. So again, this is the familiar part of the network. Here, what you have is the original paper has a picture that really helps. They dropped that from this paper, so I can maybe draw a cartoon here. So you have a set of what they call expert downs. These are the encoding or the down projecting layers, followed by a nonlinearity, followed by the expert up layers. And what happens is at inference time, you select one of these randomly and you forward pass on this. You select another one randomly for the expert down, and you forward pass, and there, and of course between these you have a nonlinearity, and out goes your output. It kind of seems crazy to do this, but there are a few things to notice. One, in terms of the amount of compute, this is identical to a system where you just have one expert down and one expert up, because you're doing just you're just running one of these. You're not aggregating across the different experts at a layer. But the part that's kind of and what you do at inference time is you average all of these. You average all of the weights of the ups and average all of the weights of the downs, and you run it once. Now the question is, since you're randomly pairing these expert downs with expert ups, how can a representation here be compatible with whatever representation an expert up is expecting? And the answer to that is consistency regularization. It's a very simple idea where you basically run this more than once. In this case, they show this being run twice, and you have a part of the loss function simply say that these distributions shouldn't be too far from each other, right? Now the question is, if you do that, why don't these all the expert? Of course, one of the ways to minimize this is for all the expert downs to collapse into the same function, and all the expert ups to collapse into the same function. Maybe the original paper addresses this. This one certainly does not. So they don't talk about why they don't collapse, or if there is a different component in the loss function that encourages diversity. Either way, what the consistency regularizer does is to discourage diversity uh, between the different experts. It's also worth noting that the choice of the expert is random and not a function of the input. Uh, I said a minute ago that at inference time, you don't have a choice. You're basically using an aggregate expert, so it's not really an expert. Uh, anyway, soft prompts. So soft prompt is this really interesting idea. It's very simple. It's surprising that it works so well. And again, it's very easy to explain this using this pseudocode. So all you do is, so if X was going to be the input to your model, you prepend it with a soft prompt that is learned. Think of this as in L by H dimensional vector or tensor that you learn. And now, when you fine tune your model for a task, your entire model remains frozen except for the soft prompt. If you were doing the purest version of soft prompt, of course, if you were to combine it with some of these other methods, then this would be one of the parts of the network that you would be learning. But in the pure version, it's only the soft prompt that changes. Again, it's surprising that this works as well as it does. So what it does is the part of the context that you would otherwise use for in context learning now is freed up. So now you can work with smaller contexts, and you have like learn um, a part of your prompt which now has your task specificity. For instance, if your in context learning was going to say something like, hey, I'm going to show you I'm going to show you n of these inputs, and I'm going to show you the correct output, and what I want you to do is to map it in this way. Instead of doing that, your the data that you fine tune the model on would train the model to make those mappings, and your soft prompt would be the one to the learn soft prompt would be the one to remember what the task is. So when you see this is what I want you to do, is what happens. So that is for, again, I'm kind of glossing over the empirical claims about each of these methods. That's because the table does a really nice job of summarizing these. And we can look at that in a minute. Prefix tuning is the exact same idea as prompt tuning, except instead of just there are two ways in which it is different. One of them is instead of just um, sending a soft prompt to the model input, you also send it to each of the layers. So here's the transform block. So each of the blocks get their own soft prompt. Another important way in which it's different is rather than learning this directly, you learn a possibly lower dimensional soft prompt followed by a feed-forward network. So these are the two things that you're learning during fine-tuning, and the actual soft prompt that results from applying this feed-forward network on the learn soft prompt is what you're concatenating to your layer inputs. So at inference time, you can throw this away. You just need to remember this as a result of your fine tuning, and just use this as if you were doing something like this, where as if you were just learning this. Now the question is, why is it easier to learn this and a feed-forward network than learning just a soft prompt directly? That is not answered in this paper. They basically simply say that the training is more stable this way than the other way, but I do not see the rationale for that from reading this, but maybe the original paper does. So that is prefix tuning. Intrinsic prompt tuning is, I find this to be kind of a crazy idea. It is still prompt tuning, but what you do is they observe that when you tune several prompts for several different tasks, let's say your prompts are 1000 dimensional, or your soft prompts are 1000 dimensional, and you fine tune it for hundreds of different tasks. Now, they observe that your soft prompts lie on a lower dimensional manifold. In other words, if you were to make a matrix of your soft prompts across different tasks, the rank of the matrix is going to be less than the dimensionality of the soft prompt, or the number of tasks, right? Or I should say, and the number of tasks. So because of this observation, what they do is they train an autoencoder. So they basically take your soft prompts, they learn to project these into a lower dimension, and project them back like an encoder and a decoder and a regular autoencoder. And then they use the lower dimensional soft prompts during inference. So this is a soft prompted model. So this is the autoencoder for it, and this is the soft prompted model. Yeah, they use the decoder. So you notice that at inference time. It's the intrinsic subspace prompt that is remembered and used. And just for clarity, this guy here is the intrinsic subspace prompt. And again, the part here that was surprising to me was that there would be enough tasks, or there'd be enough different tasks for network to do that would make a technique like this practical, but apparently that is the case. Additive methods, other approaches. Yes, so these are methods that are neither adapters nor soft prompts. A good example of this is ladder side tuning. Again, this is kind of a on the surface kind of a weird looking idea, and the idea is this. I wish they had a picture here to go with this, but I'll draw a cartoon here. But basically you have the pre-trained network, and they train what they call a ladder network on the side that is, surprise surprise, also a transformer, but each of the layers takes in the outputs of the hidden layers, the output of the internal layers of the original network as additional inputs. So basically and of course at training time, this the pre-trained network is totally frozen, and the parameters of the ladder network is what you're learning. So that is what you see here. And additionally, there is a trick that's kind of hidden here. Actually, let's look at this part first, and then I'll talk about the gate trick over here. So this part basically says what I just said, which is that you create a number of layers. Each of those layers takes in the input from the previous layer as well as the output of the corresponding hidden layer from the original pre-trained network. H underscore PTI is the corresponding. So you see that this has this, my picture is somewhat misleading. It actually has the same number of layers as the pre-trained network, because I here is the same. And yeah, that is why there's a one-to-one mapping between these hidden layer outputs. Now the trick here is really that there is also a gate that determines how much the input to the transform block is changed. So at one extreme, if this is 0, the input to the transform block is entirely this learned piece, h underscore pt times this, which is the weight of a layer here in your ladder network. And when gate is closer to 1, then it's entirely the original x. Actually, I shouldn't say original, because h underscore pt is coming from your pre-trained network. The pt stands for pre-trained, and h is the input to the network. So anyway, so this gate basically controls how much or how far it is from the pre-trained network, and that is also learned. And again, this seems to work well in practice. They compare to LoRa and so on. Next is IA3. This is interesting because of its simplicity. So you see, basically the idea is that you only learn these 3 things, which scale K, V, and the output of the feed-forward network respectively. So you're learning a very, very small set of parameters, and that seems to work really well. Again, they compare it to LoRa. Selective methods. Okay. I think I briefly mentioned bitfit before. Here you only learn you only tune the biases, and you freeze the rest of the network. and this results in, for the I don't recall for which. I guess this was for BERT. It results in training only half a percentage of the model parameters and seems to do well. Again, there are many of these approaches work for certain data sizes but not others. So it is not straightforward to compare these. Some of them are better on memory, some of them are better for certain models but not others, or for certain data sizes and not others. Diff pruning is this idea that you learn. Diff pruning importantly does not reduce either the amount of memory required at training time or amount of compute. But what it does is it essentially learns a binary mask, which it learns to select the set of weights to update. But why does it make sense? I mean, one, it works in the sense that you can fine tune using this, but the bigger reason to use this is now when you do select a set of a subset of parameters, because you're only updating those, you only need to save those. So when you have a situation where you have a large model that needs to perform several tasks, you do not need to store you do not need to store one set of parameters for each task. Sorry, I got interrupted there for a second. So I was saying, when you have a network that has to perform several different tasks, you do not need to store the entire set of weights for every task, but you can only store the corresponding smaller set of weights for every task. So you have the baseline network of all the parameters plus a small set of weights for every task. So it saves storage but not runtime memory. Freeze and reconfigure. So here basically the idea is that if you have a weight matrix, right? Think about a weight matrix, which is number of inputs to the layer times number of outputs from a layer. You identify using some pruning method a subset of rows or columns that you want to train and a subset that you freeze. And then you just do this. You basically rearrange the weights so that you can just split them in this way. So now you have F stands for frozen and T stands for trainable parameters. You train a small subset, and this is more of a meta algorithm because there are different pruning methods that you can use to figure out which ones you want to freeze and how you want to reconfigure the parameters. Right. Fisher information masks. This is also, I wouldn't say it's similar to that, but basically you select the set of parameters to update using the Fisher information index, which is given by this. Basically is trying to approximate how informative how important a parameter is. And then you update just those. But they say it is neither efficient nor does it work very well. Reparameterization based methods. So here, let's actually start by looking at LoRa because this is the easiest to understand. So what happens here is really that this again, like all of the methods, reading the pseudocode is what makes this really easy to understand. So imagine a feed-forward. Oops. So imagine part of the network that's doing X, matrix multiplication W. Now the update to W is actually done with WA and WB. It's actually done with the low rank version of the matrix, which is W factorized to WA and WB. Actually, let me try to reproduce the picture in the original paper. That will make this really easy to understand. So here, yes, plus the output. Okay. So the idea here is that if W is an n times m matrix, and n times m is a big number, a k-rank factorization of this would result in an n times k matrix plus a k times m matrix. And if you choose k to be significantly smaller than m and n, then here you have k times n plus m. Oops. Here you have k times n plus m as the number of parameters here, which for a clever choice of k can be significantly smaller than m times n. And the point here is that you still have the original W, but you're adding the x times this matrix, which is a low rank matrix, to this. And now when you train, you freeze this W and only train this. So basically the delta W is what it must be somewhere here. So basically you're learning a low rank addition to W. And this basically works really well in practice. And as you can see, this does not commit itself to a particular place in the network or anything. So this is a technique that's orthogonal to a lot of the other techniques that we talked about, and you could combine this with other techniques, which is what people have done. So Krana is another technique which is very, very similar. But what they do is, rather than using just the matrix product as the low rank approximation, they use what's called a Kronecker vector product, which results in a much more aggressive reduction in the number of parameters. So here, let me see if they do have a definition. Yes, they do have a definition here. So this is the definition of the Kronecker product. Basically, the way to read this is, you can see that given two matrices that are n by m and k by l, the resulting matrix has the number of rows in the resulting matrix is the product of the number of rows of the individual input matrices, and the number of columns is the product of the number of columns. And the way this product works is you take each of the elements of the first matrix and multiply that scalar with the entire second matrix and basically paste that block of the vector there. Which is why you get number of elements in one times the number of elements in the other. So this is a much more significant reduction in the number of parameters. So hybrid approaches. There are different hybrid approaches. All of them kind of, as the name suggests, they combine the different techniques that we have looked at. The basic ideas are the ones that we've already gone over. As the name suggests here, they mix and match, and there are different ways of doing that. And the reason I'm glossing over this is that Sorry, I got distracted there for a second. Yeah, so as I was saying, hybrid approaches combine the ideas that we've already talked about. I'd like to look at, so I'm not going to go over each one of these, but I'd like to look at Unipelt, which I thought had a very interesting take on this. So what they do is to combine uh, LoRa adapters and prefix tuning, and they do this in this learned manner, right? So for instance, here they're using an adapter. This is similar to the code that you've seen before, except you notice that the contribution of the adapter is gated by a learn function, right? Now, when your gate is close to zero, your contribution ends up being very small from the adapter. And when it's higher, then the contribution is higher. Similarly here, there is a LoRa part of the network, but it's gated by a LoRa gate, which is also learn. And the third one is prefix fine tuning. Oh, here, and that's right here, right? If you remember the prefix part of it, where part of the self-attention block gets pre-trained gate. This is the prefix tuning gate, and again, it's the same idea. So at runtime, depending on your input, your network is free to use any of these techniques. And of course, the basic idea of parameter efficient fine tuning still stays, where now you're only tuning these parameters and not the rest of the parameters. S4 is also an interesting idea where you basically define different groups of these combinations, and then you weight these different groups in a learnable manner. Again, the original paper has pictures that make it really easy to follow, but this one does not. In terms of comparisons, they do go to great lengths to compare the performance of these across different dimensions, model size, data size, number of tasks, and so on. And maybe what we can do now is to look at the tables that we glossed over in the beginning. Let me go up. Here, these are a number of trainable parameters, number of changed parameters, and what they were evaluated on. So pretty much everything has been evaluated on as a sub 1 billion. And here you have these bigger models. There are significantly fewer that are evaluated. Let's maybe try to find some interesting ones. Let's say LoRa. Yeah, LoRa is one that has been evaluated on all sizes. You end up training, this is percentage, so you end up training 0.01 to 0.5%. Again, I think this column you notice are very similar for all the methods. Whereas percentage of change varies much more. And prompt tuning, prefix tuning also have been widely evaluated. Bitfit, again, though not as impactful empirically, it also has been tried. Adapters in general have been. And now we can look at the impact on storage and memory. Yeah, I think the thing to notice is that almost all of these help with storage, because as we talked about before, now the tasks, your task specificity is in a much smaller set of parameters than the full set. So you could store weights for individual tasks, for a large number of individual tasks, much more efficiently. Memory, it's kind of, I mean, because this was the problem that these methods sought out to solve in the first place. Seeing no is more surprising than seeing yes. And diff pruning, as we talked about before. Does not help with memory because if you recall, they were learning a binary mask, if you will, to select the set of parameters to be updated. Yeah, that's pretty much it. I hope this gives you a good introduction into all of these methods, and I personally really liked this way of thinking about this. Otherwise, gleaning this insight without this picture would have been much harder. So there it is, scaling down to scale up, a guide to parameter efficient fine tuning. I hope you've enjoyed this presentation. Thank you.